In this lecture, we're going to talk about fluvial geomorphology. Now, that sounds like a real mouthful. Fluvial, of course, refers to streams and rivers, and geomorphology is the study of landforms. So, fluvial geomorphology would be the landforms associated with streams and the processes that shape streams. We'll start out here with a picture of the Laitaure Delta, which is in Sarek National Park in Sweden. I put this in because this picture really conveys a lot of action on this floodplain here. We have a river delta, so we've got the river flowing from the bottom right corner of the picture into the lake in the upper right corner. You can see this is an area with a lot of topography. The mountain sort of juts up off of the upper right hand side of the photo there. It's a big U-shaped valley. Of course it's in Sweden, so this is glacial, a glacial valley. Glaciers melted away and left this river system with the lake. And the river here has become very distributary. This happens near deltas. The main channel has split into a bunch of side channels. They're competing for water. You can see some of the channels that appear to be fairly dry, some that have lots of light blue water. That's the main channel that's carrying most of the glacial sediment that's being picked up upstream of this. And some of the other colored channels have less sediment because they're side. And then we've got the big marshy, boggy areas with lakes in between. And of course this river just meanders back and forth across here and really modifies this pretty well. You can also see, if you look down here, these ridges. These are tree lines, but they're probably natural levees that have formed along these channels during floods and so forth. So a lot of landforms to think about here. Riverbanks, levees, floodplains, terraces, all kinds of things. All right, so let's step back and think at the really big picture. How can we think about streams? Well, at a watershed scale, every drainage has its own pattern. So if we look over here on the right side of your screen, in the upper left diagram here, it says dendritic. And dendritic is because this evokes the veins in the leaf of a deciduous tree, and that word comes from that plant physiology, I guess. But this is what we typically find, the drainage pattern we typically find in areas with relatively flat-lying sedimentary rocks. So if you look at the drainage pattern of most watersheds in Missouri, say, where our rocks are predominantly flat-lying, you'll see a dendritic pattern. Below that, you have trellis. Here we have parallel main stems of streams with short tributaries. Those form where you have big ridges. So in this case, the ridges would run from the lower left to upper right corner of the picture, and the streams are draining the valleys between these ridges. Rectangular, that is where you have a bedrock. Now this could be another area like dendritic where the bedrock's flat-lying, but here we have a really strong joint control. So the bedrock has been fractured into rectangular, big rectangular blocks, and so the stream follows those breaks, those fractures, and you get a rectangular pattern. It's not hard to guess that radial and annular probably form where we have a conical mountain. Like, you can think about a big volcano. It doesn't have to be just a volcano, but any big conical mountain where you have a central high point and all the streams drain away from that central point. And then we have some weird ones, multi-basinal. We see this in areas that are really low-lying and really flat without a lot of surface drainage. So water just sort of accumulates in a lot of different small lakes and ponds with small streams that connect them. And then contorted is another odd one. You're probably never going to see anything like that, so I'm not going to worry too much about it. Partly because I can't think of any example of how the geology causes that, to be perfectly honest. The parallel pattern, which we didn't talk about there in the upper left, that is where you have a steady slope that drains in one direction. So maybe we have streams draining off of a large glacial plain that's sloping away to the southwest or lower left corner of that picture. Now on the right side here of the diagram, we have this watershed with a main stem, and each of the different tributaries has a number. The ones are the first order tributaries. These are the streams with no tributaries. So this is where flow starts. Where two ones come together, you get a 2. Where two 2s come together, it becomes a third order stream, and where two 3s come together, it becomes a fourth order stream. Now you'll notice that down here in the lower part of the watershed, a second order stream joins the fourth order stream. Now a 2 and a 4 coming together doesn't increase the stream order of the main stem. Similarly, if we had a 3 and a 4 come together, it would still be a 4 after the tributary. The only time the number increases is when two tributaries of the same order join. So two 3s become a 4, two 2s become a 3, two 1s become a 2. All right, another important geomorphic concept in streams is stream equilibrium. Streams in their natural condition typically exist in a state of dynamic equilibrium. We'll talk a little more about what exactly dynamic equilibrium means in a second, but let's just put it in a simple term first. If we think in terms of how much sediment is delivered to the channel, there are a lot of processes, geomorphic processes, along the landscape. A good example of one would be landslides or different forms of mass wasting. Those erode the sediment off of uplands. Eventually that eroded sediment, maybe the landslide slides down into the floodplain where the stream can start to access those sediments. So that would be the sediment delivered to the channel. Then we have the erosion capacity of the stream based on how much water there is in the system, how much potential energy there is in the system, and potential energy here would be how steep the slope is that the stream is flowing down. Steeper slopes are more energy. More water gives more ability to erode. So your sort of ability, your erosion capacity is controlled by that, the energy in the system and the water in the system. And those things then are related to the sediment discharge. How much sediment does the stream actually erode downstream, or if you think about a really big stream, maybe out to the ocean, into its delta or out into the ocean. So when we have an equilibrium, it's because the amount of sediment that's being delivered to the channel equals the capacity of that channel to erode sediment, which equals the amount of sediment that's being discharged out of the system. If all three of those things are in balance, then we've got a stream that's in a perfect equilibrium. If one of those is out of balance with the other, say we have more sediment being delivered to the channel than we have capacity to erode and discharge, then we're going to have to change the stream system. If we have more sediment coming in than we can move, that sediment's going to have to be stored in the stream valley, and the stream will start to aggrade or rise up. It will start to fill in its valley with sediment. We're going to come back to Lane's diagram here, Lane's balance, in a future lecture, but I want to introduce it here. This is one of the most important figures, I think, in stream geomorphology, because it shows the relationship between the amount of sediment, the size of this sediment, the amount of water, the stream slope, and all these variables and how they interact. If you look at Lane's balance and you say, okay, my stream system is getting more water, more precipitation because climate's changing, how's that going to affect sediment size, stream slope, sediment yield? Lane's balance will help you make that prediction. We'll come back to this and look at that in more detail later, but this is a good model. It's sort of like the Vicqua stick that we visited in our last lecture. Okay, a little more on stream equilibrium. I mentioned that there's a dynamic equilibrium in the definition on the last slide. A dynamic equilibrium means that as the system is pushed or pulled by these different watershed factors, let's say climate is delivering more water. Well, if there's more water in the stream system, the watershed's geomorphically going to have to respond to that. If there's more water and nothing else changes, we may have a net increase in erosion, which means the channel may actually incise into the floodplain as it eats away the sediment at a greater rate than sediment's being delivered from the adjacent hill slopes. So in that case, the dynamic equilibrium would be that you have a change, a climate change, and that affects a change in the hydrology, which affects a change in the geomorphology. So every action causes a reaction. Um, a steady state equilibrium would be where none of those watershed factors are ever changing. Climate steady, topography steady, geology steady, soils are steady, all those things are the same. There's still going to be variation because even if you've got a climate that's not changing, we have wet years and dry years, we have wet months and dry months. And so sometimes we'll have greater stream flow, which means greater erosion capacity, but then in a drier year we may have less stream flow and less erosion capacity, and it averages out over time, and the average of those lines stays steady. In the steady state equilibrium there, the line stays horizontal. We're not going to worry about static equilibrium or dynamic metastable equilibrium. They're not really relevant to the stream systems we're going to study this semester. Okay, let's talk a little bit about floodplains. This is one of the geomorphic features, the landforms of streams. In a floodplain, we can think about the hydrologic floodplain. This is the portion of the floodplain that the stream may actually be using. Sometimes the topographic floodplain is larger than that. And the photo here on the right sort of shows that. You can see the active channel here, but then you can see a lot of cut-off meander bends. So this channel is really, this is a stream in Alaska. It's up there in the wild areas. There's no human control of this stream, no human interference. It's just sort of chugging along, doing its thing, and it's very dynamic. You can see that that channel is very sinuous, a lot of meandering. We've got the old cut-off meanders where the stream channel used to be that are now oxbow lakes here and there. And you get a sense that if we sort of draw a line from this side to this side of those active meanders, that's the hydrologic floodplain. That's the portion of the floodplain that the stream is actively using. Now, if you look very closely at this figure, it looks like maybe the topographic floodplain extends way out here to the right, and I can't even tell where it ends over here on the left. But the stream's not really using that, so that's the difference between this hydrologic and topographic floodplain. The bottom figure here just shows some of the, as a cartoonist, some of the things we're seeing in the photograph on the right of these meander scrolls, these areas that are old filled-in meanders, the oxbow lakes, which are recently abandoned meanders, some of the splay deposits where floods have spilled water over bank and deposit streams. This may be a splay deposit right here in this stream, or maybe during a flood the water spilled out on the floodplain and deposited some sediment there. Okay, so that's floodplains geomorphology. Now we can talk about the longitudinal zones of a stream. So longitudinal would be the upstream to downstream dimension of the stream. Geomorphically, we can divide a stream into 3 longitudinal zones. The headwaters area. Headwaters areas are typically steep. So we have steep slopes, lots of energy, so the stream is able to erode a lot of sediment really fast. We typically get big sediments in these headwaters areas. Now in the picture it shows mountains. They don't have to be mountains. A headwater stream in Missouri doesn't necessarily start in the mountains. It just starts in the highest area of the landscape. Then we have the transfer zone. The transfer zone is the area where all the sediment that's being eroded out of the headwaters because of all the excess potential energy out there is being transferred through this zone through to the depositional zone that's the next one downstream. Here we have lower elevation streams, gentler slopes. Usually we get broader valleys, water valleys, and the river begins to meander because there's less potential energy, so the stream starts to spend energy going sideways back and forth, moving sediment around, instead of focusing its energy vertically into cutting down the landscape like it does up in the headwaters area. The last zone is the depositional zone. Now this is a zone that's really low elevation, so we're down close to base level. If this were the Mississippi River, this would be the part of the river that's sort of south of Cape Girardeau, south of the Boot Heel of Missouri, all the way down to the mouth of the Mississippi River where it enters the Gulf. Really low slope, really big meanders. The stream makes these big meanders back and forth. Not much erosion is happening there. It's really net deposition from all the sediment coming upstream is being stored temporarily in the depositional zone as it can slowly be moved out to sea or out to whatever the base level is. Here's a picture of a headwater stream. This is a stream in Maryland. It's a picture I took a few years ago. You can see it's fairly steep. You can just see by eye that the water's falling pretty quickly through this reach. You can see the big sediment there. You can even see sort of the texture of the water surface, that there's a lot of riffles here, a lot of energy in this stream. Here we have a picture of a transfer. This is a picture I took of a stream in southeastern Minnesota. We're in that area where we're not quite in the headwaters. The stream's a little larger. You can see here that the stream is actively meandering. It's moving sediment. You can see some sediment on the bank that's on the right side of the picture there that's been deposited by a recent flood. So this is a typical transfer zone picture. And then lastly, this would be sort of that depositional zone. You can see how big these meanders are. Great big meanders. They cut themselves off. If we look here, eventually in this area, the stream is going to try to take the shortcut around this bend as it erodes this gooseneck from both sides. It'll cut that off, and this meander will become abandoned, just like this one already has. Once it's abandoned, we call it an oxbow lake. Now, these oxbow lakes, what happens are, because they're not actively being maintained by erosion in the active stream channel, they fill in rather rapidly with sediment that comes in from floods, and as the biology sort of adds up in there, and they go from sort of lake to marsh to pretty much filled in. And it's not, looks like maybe up here in the upper left-hand corner of the picture, you can see this oxbow is almost all the way healed in. That first picture, one of those first pictures we looked at, the actively meandering stream in Alaska in an earlier slide, was a really good example of all the different stages of oxbow lakes. You might want to go back and look at that. Here we have just a comparison of some of these channel forms. So in the transfer zone, we might have a straight channel that's got some sinuosity. You know, so it's starting to meander, but they aren't really deep meanders. We get pools and riffles forming. We get some alternating point bars. We'll ignore braided channels for the second. The meandering channel with a great sinuosity, this would be like in the erosional zone. Here we get really big meanders that go back and forth, very active. And then a braided channel's, it's not really intermediate. This picture is a little misleading in that way. A braided channel is not intermediate between a slightly sinuous straight channel and a deeply sinuous meandering channel. The braided is a special case where we have a greater sediment supply than we have ability to erode that sediment. So the stream can erode the sediment as rapidly as it's being brought into the stream from the adjacent uplands, and so it has to store that with a lot of sediment bars out in the active channel. These are very active. Typically they don't have any vegetation on them because they're constantly being moved around, eroded, and redeposited and so forth. All right, so that concludes our brief introduction here to stream geomorphology. We'll pick up the next lecture with hydrographs.